Hey guys, so in this video we're going to be taking a look at how we do arithmetic with the complex numbers. So by that I mean how we add, subtract, multiply and divide complex numbers. But just as a quick recap of last time, we talked about how there were two parts to a complex number, namely a real part and an imaginary part. So if we take any complex number, say a plus bi, then the real part of our complex number is going to be a, while the imaginary part is going to be b. Okay, now we're going to take a look at something called the conjugate of a complex number. Now it's really simple. If we have any complex number which we'll call z, or in other words a plus bi, then the conjugate of z is equal to a minus bi. So we just take our complex number, which we write down as a z with a bar on top, and we make the imaginary part b negative. So for example, if we have the complex number 1 plus 3i, then the conjugate of 1 plus 3i is 1 minus 3i. Now this might seem a little bit random, but trust me, it will make sense in a minute. Right, so now we're going to take a look at how we add two complex numbers. So say we want to add 1 plus 2i and 3 minus 7i. What we do is we simply put the real parts together on one side, which is the 1 and the 3, and we put the imaginary parts on the other side, which is the 2i and the minus 7i. So as you can see, we haven't actually changed anything here, but now we can combine the 1 and the 3 to make 4, and we can do the same for the 2i and the minus 7i to get negative 5i. So when we add 1 plus 2i and 3 minus 7i, we get a new complex number, which is 4 minus 5i. Now in general, when we add two complex numbers a plus bi and c plus di, we just add their real parts together, which is a and c, and then we add their imaginary parts together, which is the b and the d. So we get a plus c plus brackets b plus d times I. Subtraction is almost exactly the same as addition. Let's say we want to calculate 3 minus 6i minus 8 minus 9i. So firstly, let's get rid of the brackets. So it becomes 3 minus 6i minus 8 plus 9i, because the negative here times the negative here makes the 9i positive. And now we just add up the real parts and add up the imaginary parts. And so we get 3 minus 8, which is minus 5, and negative 6i plus 9i, which is 3i. So we get minus 5 plus 3i. Now in general, if we take any complex number a plus bi and we subtract c plus di, what we'll get is a minus c plus, in brackets, b minus d times I. To multiply two complex numbers together, we expand and collect. So for example, let's multiply 1 plus 2i and 3 minus 4i. Using the FOIL method, we'll get 1 times 3, which is 3, plus 1 times negative 4i, which is negative 4i, plus 2i times 3, which is 6i, and lastly 2i times negative 4i, which is negative 8i squared. Now we can tidy this up a bit to get 3 plus 2i minus 8i squared, but now we've got an I squared term to deal with. So how do we get rid of this? Well, remember from before that we said that I squared was equal to negative 1. So we can actually replace this I squared term with negative 1, and so we'll get 3 plus 2i minus 8 times negative 1, which is 3 plus 8 plus 2i, which equals 11 plus 2i. So using this method, we can actually multiply any two complex numbers together. In general, if we take a plus bi and c plus di, and then we multiply them, what we get is ac plus adi plus bci plus bdi squared. And by combining the middle terms together and changing the I squared into a negative 1, this simplifies to ac plus, in brackets, ad plus cb times I minus bd. Or in other words, ac minus bd plus, in brackets, ad plus cb times I. Multiplication is also when the conjugate of a complex number comes in handy. To see this, let's take any complex number, say 3 plus 4i, and we're going to multiply it by its conjugate, 3 minus 4i. So expanding will give us 9 minus 12i plus 12i minus 16i squared. And notice here that the imaginary terms minus 12i and 12i are actually going to cancel themselves out, while the real parts are going to add up to make 25. In fact, when we take any complex number and we multiply by its conjugate, its imaginary parts will always cancel out, and so we'll always get a number that's completely real. To prove this, let's take any complex number a plus bi, and we're going to multiply it by its conjugate a minus bi. So expanding will give us a squared minus abi plus abi minus b squared times I squared. And again, the imaginary parts are going to cancel out, Well, this I squared is going to turn this into a positive b squared. So we'll get a squared plus b squared. And since a and b are both real numbers, a squared plus b squared is clearly also going to be a real number. Division of complex numbers is a lot more interesting. Let's try to divide 3 plus 5i by, say, 1 plus I. The problem here is that we have a complex number on the bottom, so how can we get rid of this complex number and make it purely real? Well, using what we just learnt before, we can multiply 1 plus I by its conjugate, 1 minus I. But to make sure that I'm not changing the fraction itself, I also have to multiply the top by 1 minus I, just so that it all balances out. So now we get 3 plus 5i times 1 minus I divided by 1 plus I times 1 minus I. Now expanding all of this gives us 3 minus 3i plus 5i minus 5i squared, all divided by 1 minus I plus I minus I squared. Now looking at the top for an instance, we've got minus 3i plus 5i, which is just 2i, and this minus 5i squared is going to become just 5. Now on the bottom we've got a minus I and an I, which are going to cancel out, and this minus I squared is just going to become 1. So we have 1 plus 1, which is just 2. Now 3 plus 5 is 8, so we've got 8 plus 2i divided by 2. 8 divided by 2 is 4, and 2i divided by 2 is I. So that means our answer is 4 plus I. Now this method will work when you need to divide any two complex numbers. And to prove this, we're going to need some more paper. To prove this, we're going to consider the general case. So what happens when we try and divide any complex number a plus bi by any other complex number c plus di? So using our trick before, we're going to multiply the top and the bottom by the conjugate of c plus di, which is c minus di. And doing that will give us this kind of looking fraction. And now expanding that is going to give us ac minus adi plus bci minus bdi squared, all divided by c squared minus cdi plus cdi minus d squared I squared. Anyway, so on the bottom, these two imaginary parts are going to cancel out. And the I squared here is going to make this BD positive. So on the top, we're going to have AC plus BD plus, in brackets, BC minus AD times I. And then on the bottom, we're just going to have simply C squared plus D squared. And now decomposing this into two fractions, we're going to get AC plus BD divided by C squared plus D squared plus, in brackets, BC minus AD divided by C squared plus D squared times I. Now because these horrible looking fractions don't actually have any i's within them, that means they're always going to be completely real. And that means we've solved it. We found the general case when you divide a plus bi by c plus di. And it's this horrible looking thing right here. So granted, it's not very pretty, but at least we know that using this method, it's going to work every time. The last thing to look at in this video is what happens when you raise the number I to a power. So for example, we already know that I squared equals minus 1, but what about I cubed and I to the power of 4, and so on? Well, there's a little trick you can use for these. Let's firstly look at I cubed. Notice that I cubed is equal to I squared times I. And since I squared is equal to negative 1, that means that I cubed is equal to negative I. Now as for I to the power of 4, I to the power of 4 is just I cubed times I. But we know I cubed now. I cubed is negative I. So that means this is negative I times I, or in other words, negative I squared. And negative I squared is just going to be 1. So I to the power of 4 equals 1. Now we could keep going and find I to the power of any power using this method. But if we were to make a list of these, what we'd find is that I to the power of 0 equals 1, I to the 1 equals I squared equals negative 1, I cubed equals negative I to the power of 4 equals 1, I to the power of 5 equals I to the 6 equals negative 1, I to the 7 equals negative I to the 8 equals 1, and so on. Now hopefully you can see the pattern here, because what we really have is a 4-step pattern that repeats forever of 1 I minus 1 minus I. Now this means for whatever number you pick, I to the power of that number is always going to either be 1, I, -1, or -i. But how can we tell which one it is? Well, let's try an example. Let's try I to the power of 272. Now notice that 272 is an even number. That means we can write it in the form 2 times 136. So in other words, we have I to the power of 2 times 136, or if you know your index laws, that's the same as I squared to the power of 136. But we know I squared is -1. So that means we really have -1 to the power of 136, and we can work this out, this is just 1. So that means I to the power of 272 is just 1. And in general, this method will always work if your index number is even. But what if it's odd? Well, if it's odd, we actually use the same method that we use to find I to the power of 3 and I to the power of 4. So let's take an example. Let's take I to the power of 271. Now notice that using our index laws, we can rewrite I to the power of 271 as I to the power of 270 times I. Now we can't do much about this I, but the I to the 270 we can, because 270 is an even number. So using our method before, we'll rewrite this as I squared to the power of half of 270, which is 135. Now I squared is -1, so we just have -1 to the power of 135 times I. And now we know what this is just -i. So I to the power of 271 equals -i. And this is what we do when we're dealing with an odd number. We rewrite it in the form where it's I to the power of an even number times I. And then we work with just the even number, and then we add the I on at the very end. And now using one of these two methods, we can find I to the power of any number. Okay guys, that's it for this video. Next time we'll be taking a look at how we do more things with the complex numbers, including how we find the square root of a complex number. See you then.